Hello students, welcome to memoneet. This is Ravikant, the physics teacher, and today we are going to discuss the question paper for BPT 13, which is related to mechanical properties of solid and fluids. Right? So let's look into the question number one. The first question says that select the wrong definition. First definition is of deforming force. Deforming force, the force that changes the configuration of the body. Right? So this is the correct. Right? Because deforming force means deforming means changing, the changing force. It's a force which changes the shape of the body is known as deforming force, right? Second is elasticity, property of regaining the original configuration. Yes, this is also correct. The property of the body is to regain its original configuration once the deforming force is being removed is known as elasticity, right? Next is the plastic body which can be melted. Plastic body, no. Plastic body is a body which do not have any elasticity. It means once the deforming force is being applied on it, it will change its shape completely and it will never regain it. So that type of body is known as plastic body. Does not mean that it can be melted easily. So this statement is wrong. And then coming to the fourth statement, the elastic limit beyond which the material begins to flow. Yes, elastic limit is the limit of the force beyond which if the force is being applied, then the body will not regain its original position, original shape, and it will start flowing. It will keep on changing its shape. So according to this, the correct option for this question is option C, that is plastic body is the wrong definition. Now let's come to the question number 2. It says that the equal mass of two substances of density rho, 2 rho and 4 rho are mixed together. The density of the mixture will be. See, there are say of two same masses. So if they are mixed, let the mass of one substance be m. So if they are mixed, the total mass will be equals to 2m, right? And the total volume will be equals to V1 plus V2, right? So V1, what we can say that V1 is we write it as V1 can be written as density is equals to mass upon volume. So volume is equals to density upon mass upon density. So mass upon density is 2 rho. This is V1 plus V2 is again the mass is same upon 4 rho. This is V1 plus V2. Right. Now this is V1 plus V2, and if the bodies are mixed, the total mass will be 2m, and let the new density will be rho dash. Rho dash, right? Or rho, we can write rho m, rho of the mixture. So this is the new volume. This is the new volume, that is mass upon density is the new volume, and this is also the new volume. So we can equate the two. That is 2m upon rho of mixture is equals to m upon 2 rho plus m upon 4 rho. So m can be taken common and cancelled out, and then finally when we calculate from here, we get rho of mixture is equals to, you can see from here the calculation, rho mixture is equals to 8 rho by 3. So the correct answer for question number 2 is 8 rho by 3, right? So when the two substances of equal mass but different densities are mixed together, the equivalent or the resultant density will be equals to 8 rho by 3. Now let's come to question number 3. Question number 3, so the correct answer for question number 2 is option C. Now let's come to question number 3. Question number 3 says that a force is needed to break the copper wire having radius r. The force needed to break the copper wire of 2 times the radius. See, the force required to break the wire or any longitudinal thing, that force is directly proportional to the area of cross section, right? Is, we can say, is area is pi r square. So we can say that force is directly proportional to r square, that is radius. So if radius is being doubled, the force will become 4 times. So the correct answer for question number 3 is option C, that is the force required to break a copper wire of thickness of radius 2r will be equals to 4f if f is the force to break the copper wire of radius r. Right? Now let's come. So correct answer for question number 3 is also option C. Now let's come to question number 4. Question number 4 says that there is a small hole in the hole of area A at the bottom of a cylinder vessel. Water is filled up to a height h, and water flows out of it in t seconds. Now, if water is filled to a height 4h, it will flow out of it in time equal to. So see, the time of emptying the container is directly proportional to under root of height up to which the liquid is being filled. So from here we can say that T1 upon T2 is equals to under root of H1 upon H2, right? So from here we can say that T1 is your T and T2, let it be T2, is equals to under root of H1 if H1 is H and H2 is 4H. So from solving this we will get that T2 is equals to 2 times of T. So the correct answer for this question will be question number 4. The correct answer will be option C. That is time in emptying a container of having water to height 4 times of H will be equals to 2T, right? So the basic thing which I've used here is the time of emptying the container is directly proportional to the root of the height up to which the liquid is filled in the container, right? Now let's come to question number 5. Question number 5. On increasing the length by 0.5 millimeter in a steel wire of length 2 meter, the area of cross section 2 millimeter square, the force required is. So they are asking you force. So from here we will be using the Young's modulus, the formula for Young's modulus. Formula for Young's modulus says that Y is equals to stress upon strain, and stress is force upon area. Strain is change in length upon original length. So from here we get that Young's modulus is equals to F into L upon A delta L. Now, in this equation, we have the value of Young's modulus, we have the value of length, we have the value of area of cross section, we have the value of delta L, and the value of F is unknown. So, simply putting the values in the correct unit and solving it, we will get the answer. So, putting the values here, we can see in the calculation, putting the values and getting the calculating it, we get the answer as F is equals to 1.1 into 10 to the power of 2 Newton. So, correct answer for question number 5 is option D, that is 1.1 into 10 to the power of 2 Newton. Simply it is formula based question. To put the value and get the answer. The formula used here is equals to Y is equals to stress upon strain, that is Young's modulus is equals to stress upon strain. So it can be written as rearranged and written as Y is equals to F into L upon A into delta L. Right. So the correct answer for question number 5 is option D. Now let's come to question number 6. Question number 6 says a body floats in water with 40% of its volume outside the water. When the same body floats in the oil, 60% of its volume remains outside the oil. The relative density of the oil is. Let's first understand the relative density of any substance is density of the substance upon density of water. Right? Second thing which you need to understand is the fraction of the body inside the liquid is equals to density of the body upon density of the liquid, right? So if the liquid is water, we can say that the fraction inside will be equals to density of the body upon density of water, which is nothing but relative density of the body, right? Now in the question they say that the 40% of the volume is outside in water. So for the case 1, for the first case, fraction inside will be equals to 60%, that is 0.6, because 40% is outside, so 60% is inside. So the fraction inside is equals to 0.6. We can say that this is equals to density of the body upon density of water, right? Now, if we talk about the second case, in the second case, when the body is immersed in oil, again the fraction inside is equals to 0.4. 0.4 why? Because it is 60% outside. So the percentage inside is 40%. So the fraction inside will be 0.4. So in this case, fraction inside is 0.4, and this will be equals to again the density of the body upon density of oil. Density of body upon density of oil. What we need to calculate is the relative density of oil. What is relative density of oil? Relative density of oil will be density of oil upon density of water, right? So if I divide this quantity with this quantity, that is, if I write density of body upon density of water divided by density of body upon density of oil, this will result in density of oil upon density of water. So this holds a value of 0.6 and this holds a value of 0.4. So this will be equals to 0.6 upon 0.4. So from here we get density of oil upon density of water is equals to 0.6 upon 0.4, and that would be equals to 1.5. So the relative density, and this is nothing but the relative density of oil. The relative density of oil will be equals to 1.5. So the correct answer for question number 6 will be option D, that is 1.5. I hope the solution is clear here. What I'm trying to tell you here is, first thing is the density, relative density of any substance is density of the substance upon density of water, right? When a body is immersed in a liquid, the fraction inside using the Boyle's law, we can say that the fraction inside the liquid is equals to density of the body upon density of the liquid, right? So density of the body upon density, and if the liquid is water, it will be equal to relative density, means fraction inside will be equal to relative density if the body is immersed in the water. Now, for the first case, when the body is immersed in the water, it has 40% of its volume outside the water. So the percentage inside the water is equals to 60%. It means fraction inside the water is equals to 0.6. And I told that fraction inside is equals to density of body upon density of liquid. So density of body upon density of water is equals to 0.6, right? Now, in the second case, when the same body is immersed in oil, the 60% of the volume is outside. So the percentage inside is 40%. So the fraction inside is equal to 0.4. Now 0.4 is again density of object upon density of the oil. So density of body upon density of oil is equal to 0.4. Now we have first, that is density of body upon water is equal to 0.6. Second, we have density of body upon density of oil is equals to 0.4. When we divide these two, we'll get density of oil upon density of water. When we divide these two, we'll get density of oil upon density of water, and that would be nothing but relative density of oil. And this is equals to 0.6 upon 0.4, and so the relative density comes out to be 1.5. So relative density of oil is 1.5, and hence the correct answer for your question number 6 is option 4, right? Now let's look into question number 7. Question number 7 says that a copper wire and a steel wire of the same diameter and length are connected end to end, and a force is applied which stretches their combined length by 1 centimeter. The two wires will have different stress and strain, the same stress and strain, the same strain but different stress, the same stress but different strain. See, stress is force upon area. So because equal force has been applied and both have equal diameter, same diameter and length, and applied, and a force has been applied, they are connected together, so the same force has been applied and they have equal diameter, so they have equal area of cross section, therefore the stress will be same. But because the two wires are made up of two different materials, so their Young's modulus will be different, therefore the strain in the two wires will be different. So according to this, different stress and strain, no, the same stress and strain, no, the same strain but different stress, no, they have the same stress but different strain, because the material is different, so strain will be different. So according to this, the correct answer for question number 4 is option D, right? So let's look into question number 8. Now question number 8, Question number 8 says, Question number 8 says the surface tension of the soap is 4 into 10 to the power of minus 2 Newton per meter. If soap bubble of radius 10 centimeter is blown, then the amount of the work done is right. So the work done when the soap bubble is blown is W is equals to 2AT, where A is the not the cross section area. A is the surface area. So surface area will be equals to 4 pi r square, right? Now radius is equals to 10 centimeters, so it will equals to 0.1 meter. Now surface tension T is given as 4 into 10 to the power of minus 2 Newton per meter, and we have the formula T is equals to 2AT. We need to calculate the work done, so W is equals to 2 and A we have as 0. So we have the radius, we can put 4 pi r square. So W is equals to 2 into 4 pi r square into T. Simply putting the values 4 pi and r is equals to 0.1, r is equals to 0.1 and into T. Solving this will get our work done is equals to 3.2 pi m, that is millijoule, 3.2 millijoule. So the work done for this is the correct answer for question number 8 is option 1, that is 3.2 pi millijoules. Simply what we have used is the formula W is equals to 2AT. Work done is equals to 2 times of surface area into surface tension, and this would give us this, the work done. From where have we got this formula? We have got this formula from the formula that the surface tension of a body is equals to work done upon change in area, right? So work done will be equals to tension into area. Tension into area. Now why? Because why 2 here? Because the soap bubble has two surface areas, one inside and one other outside. So we have multiplied it with 2. Whatever is the change in the area will be on both the sides. So we multiplied by 2 in the solution. So we get W is equals to 2AT. Now we have the values of A, we have the value of T. Putting it, we will get the work done. So according to the calculations, the correct answer for question number 8 is 3.2 pi millijoule, which is option A. So the option A is correct answer for question number 8. Now coming to question number 9, it says assertion, the bridge were declared unsafe after a long use. Reason, the elastic strength of the bridge loses with time. Both the statements are correct and the reason is also correct, right? Because with the time, what happens, the property of the body are lost. So the elastic property of the body is also lost. So as the time passes away, the bridge loses its velocity, its property of regaining its shape, and can get deformed easily. So once if it gets deformed, it is unsafe for use. Therefore, the bridges were declared unsafe after a long use, right? And it is because they lose their elastic property. So the assertion is correct, reason is correct, and reason is the correct explanation for the assertion. Therefore, the correct answer for question number 9 is option A, that is both assertion and reason are correct, and reason is the correct explanation for assertion. Alright, now the question number 10. Coming to question number 10 says that a blood is flowing at the rate of 10 centimeter cube per second in the capillary, and the cross section area itna, that is 0.1 meter cube. The velocity of flow is, alright. So rate of flow of blood is given as Q is equals to 100 centimeter cube per second. The area of cross section is given as A is equals to 0.1 meter square, that is equals to 0.1 into 10 to the power of 4 centimeter square. We are converting it into centimeter square because the rate of flow is also given in CGS system. Now let the velocity of the flow is equals to V. We are taking the velocity of the flow is equals to V using the equation of the flow of liquid in terms of the area and velocity. This rate of flow is equals to area of cross section into velocity. Area of cross section into velocity. So Q is equals to A into V. We have the value of Q, we have the value of A. We can easily calculate the value of V by putting the values. So putting the values, we get A is equals to 1 millimeter per second, right? So in question number 10, we are using the formula is that rate of flow of liquid is equals to area of cross section into velocity. We have the value of Q given in the question as 100 centimeter cube per second, and area of cross section is given as 0.1 meter square. We can convert it into the same unit and put the value and get the answer of velocity, and we are getting velocity after calculation as 1 millimeter per second, which is option A. Option A is 1 millimeter per second. So the correct answer for question number 10 is 1 millimeter per second. Now the second, let's get into question number 11. Question number 11 says that the arrangement of the three metallic rods riveted to each other is shown in the figure. Alpha for aluminium is the coefficient of linear expansion for aluminium, and alpha S is the coefficient of linear expansion for steel. Now they have given that the coefficient for expansion of aluminium is greater than coefficient of expansion for steel, means aluminium will expand more than the steel for the same change in temperature. Now if this is the arrangement, the tensile strength is developed in aluminium rod, compressive stress is developed in the aluminium rod, no stress is developed in the aluminium rod, data is incomplete to decide. Right? What we can see that aluminium will try to expand, right? Steel will also try to expand, but it cannot expand as much as aluminium is. So what will happen? There will be a resistive force acting in this direction. That is, the steel will resist aluminium to what? To expand, right? So from both the sides, the steel, because of its less expansion, will resist aluminium to expand, and because the forces are acting in such a manner as I've drawn over here, this is nothing but compressive force. So according to this logic, the correct answer for question number 11 will be option B, that is compressive stress is developed in the aluminium rod, right? Al- tensile stress means the stress along the length. So this would not happen, right? No stress, no, it's not possible that no stress is developed, right? So the correct answer is option B, that is the compressive stress is developed in the aluminum rod. Why? Because steel on the both the sides is not expanding as much as the aluminum is expanding, so it will offer some resistive force, you can say. It means that is it will resist aluminum to expand much, and that would be compressive force for aluminum. So the correct answer for question number 11 is option B, that is the compressive stress is developed in the aluminum rod. Now let's come to question number 12. Question number 12 says that the two soap bubbles of different radii are connected by a tube. Then the air flow from bigger bubble to the smaller bubble till the size become equal. Air flow from the smaller bubble to the larger bubble till the size of the size interchanges. There is no flow of air. Air flows from a smaller bubble to the larger bubble. So air flows from the smaller bubble to the larger bubble. Why? Because the pressure inside a bubble is given as is inversely proportional to the radius. Inversely proportional to the radius. Now because it is inversely proportional to the radius, it means smaller is the radius, more is the pressure inside the bubble, right? So the smaller bubble, the pressure will be more. So if a bubble with a smaller radius is connected with a bubble with a greater radius, pressure is high over here, so pressure is low over here. So obviously the air will flow from the smaller bubble to the larger bubble. So the correct answer for question number 12 is option D, that is A. Air flows from the smaller bubble to the larger bubble, right? So the pressure inside a bubble is given as P excess pressure. Excess pressure is given as P is equals to 2T by R, right? 2T by R. So we can see that pressure is inversely proportional to R. Therefore, option D is the correct answer for question number 12, right? Now let's get into question number 13. Question number 13 says an Indian rubber cord L meter long and area of cross section A meter square is suspended vertically. Density of rubber is d kg per meter cube and Young's modulus of the rubber is E Newton per meter square. If the wire extends by 1 meter under its original weight, the extension, it's not 1, it's L, right? Uh, L meters under the own weight, then the extension is, right? So again we'll use here the Young's modulus, formula for the Young's modulus. See, a small differential element dx at a distance x from the bottom of the cord, then the force acting will be m by l into x. Means what they are saying is, if m is the mass, total mass of the cord, and l is the length, so m by l will be mass per unit length. Now, if suppose this is the rubber and we are taking this portion as a small portion x, right? So mass of this would be equals to mass per unit length into the length of the portion, that is x. So this is the mass into g is weight, and this weight is acted upon this rest of the length, which will result in the change in the length, right? So if the extension in the element is dl, that is this is the change in length, right? If this is the change in length, then dl by dx is equals to fa by fa e, that is f by a into e. That is what they are saying here is, see, y is equals to f by a upon delta L by L. Now this delta L by L can be written for this situation as F by A upon BL by dx, dl by dx. Here in the question they have given Young's modulus y as E. So we will write it as E is equals to F by A upon dl by dx. So from here we can say that dl by dx is equals to f upon e a, right? That's what they have written here is dl by dx is equals to f upon e a. What is f? Force is, this is f, this is f, that is mass per unit length into length which we are considering as a weight into g. So in place of f we write m by g, m into g upon l into a into x, right? M g x upon l a e, right? Now integrating both the sides, cross multiplying and integrating both the sides, we will get L is equals to mgl square upon 2lea. So it will be mgl upon 2ae. Now if density is d, then rho is equals to mass upon volume. So here we have mass upon volume m by la, right? So putting this value from here, putting this as density, we get L is equals to dgl square upon 2e. So it will be in dgl square upon 2e. So correct answer for question number 13 is option B, right? So if we see over here, they are integrating this, that is mg upon lea is constant. Integrating x will give you x square upon 2, right? And the limits are from 0 to L, so it will be L square upon 2. So if we finally get the change in length, the change in length L is equals to mg L square upon 2lea, right? 2lea, and mass upon volume is nothing but density. So La contributes to volume and here m contributes to mass. So mass upon volume will give you density, and this quantity is being replaced by density, right? So we get the formula as change length is equals to dgl square upon 2e, which is an option 2 for question number 13. So the correct answer for question number 13 is option 2, right? Now let's come to question number 14. Now question number 14 says that what is the velocity v of a metallic ball of radius r falling in a tank of liquid at instant when the acceleration is one half that of the free falling body. The density of the metal and the liquid are rho and sigma respectively. The viscosity of the liquid is eta, right? So this is, see, the force acting on the balls are in the upward direction is the viscous force and the buoyant force, right? These are the two forces acting in the upward direction. In downward direction, weight is acting, so it is mg. Now let dm be the density of the metal and dl be the density of the liquid, right? So when the metal ball falls into the tank, its acceleration is equals to, as given in the question, It is A is equals to G by 2. A is equals to G by 2. They say that the falling tank, when its acceleration is one half that of the free falling body. So when the acceleration comes to this value, so net force is equals to m into a. So net force experienced by the body is equals to m into a, right? Where m can be written as density of the body into volume of the body, that is 4 by 3 pi r cube, and a is equals to g by 2. This is the value of a. This is the value of m, right? This is m and this is a. Now let v be the velocity of the metal ball. Therefore, the net force on the ball becomes mg minus fv minus fb is equals to ma. Means ball, this is the ball, mg is the weight of the body, fv is the viscous force, fb is the buoyant force. This is the free body diagram, and still the body is accelerating in downward direction, right? It is falling. So from here we can say what? mg minus fb minus fv is equals to m into a, sorry, is equals to m into is equals to m into a, right? That's what we have written here. Now m, we have the value of m as density into 4 by 3 pi r cube. So we put it as d is equals to 4 dm into 4 by 3 pi r cube, right, into g, minus viscous force is given by Stokes law, that is fv will be equals to 6 pi eta rv, right? And buoyant force is given as fb is equals to volume of the substance into density of the liquid into v rho g, right? V rho g. So v is equals to 4 by 3 pi r cube, density of the liquid is dl and g. Solving this, we get v is equals to dm minus 2 times of dl into r square g upon 9 eta. dm is rho and dl is sigma. So putting these values, we get v is equals to rho minus 2 sigma r square g upon 9 eta, which is in your option 1, right? Option 1. So the correct answer for question number 14 is option 1. Again, this is simple concept based, that is, if you draw the free body diagram, we can easily get the equation. What is the free body diagram? See, when the body is falling in the, oh, when the body is falling in a container, it when interacts with the liquid, the forces acting on it is, the very first force we know is the weight of the liquid. When it is moving in the liquid, it will experience the viscous force in the upward direction, and because it is immersed in the liquid, it will experience the buoyant force, right? Buoyant force is equals given by rho v rho g. Viscous force is given by 6 pi eta rv, and mg is mg. So mass is written in terms of density. F and fb and fv are given the values and then finally calculated. We get v is equals to option A. So the correct answer for question number 14 is option. Now let's come to question number 15. Which one of the following is the Young's modulus of the wire having the stress strain curve shown in the figure? So stress strain curve shown in the figure. Stress upon strain. So see, your Young's modulus is equals to stress upon strain, right? Now stress upon strain, it means from this graph we can say y upon y-axis upon x-axis. Y-axis upon x-axis means your slope of the graph. So slope of the graph is equals to this, y-axis is 8, and on x-axis for the same range we have 4. is 4. It is 8 into 10 to the power of 7, and it is 4 into 10 to the power of minus 4. So this will give you 2. So 2 into 10 to the power of 11, right? Let's see, do we have this in our yes, we have it. So the Young's modulus for this graph will be option D, that is 2 into 10 to the power of 11, right? So this is question number 15. Question number 15 has its correct answer as option number 4, option D, that is 2 into 10 to the power of 11, right? Simply calculating the slope of this stress strain diagram, simply the slope of this stress strain diagram will give you the Young's modulus, right? Why we are calculating the slope? Because by Stokes law, for the Stokes law, the stress is directly proportional to the strain, right? So stress is directly proportional to strain, and stress upon strain is a constant, and that constant is nothing but the modulus of elasticity. And here the modulus of elasticity is the Young's modulus. So simply calculating the slope of the stress strain graph will give you the value of y, that is Young's modulus. Now then question number 16. Question number 16 says that when 10 to the power of 6 smaller drops of the liquid are combined to form a new bigger drop, then its density will decrease, its density will increase, temperature will increase, temperature will decrease. See, because the liquid remains the same, density is not going to change. So density neither decreases nor increases. Now let's talk about the temperature will increase or temperature will decrease. See, what is happening is we have the formula T is equals to W by A. When several droplets are combining together, a small drop has its surface area small. Now when they are combined, the surface area has increased. Now if surface area has increased, if we rearrange and write this, we will get W is equals to T into A. So if A increases, W also increases, right? Now, if W increases, it means some work has been done, therefore, it means some energy has been imparted, therefore, the temperature will increase. So, option C is the correct answer, right? Option C is the correct answer. That is, if some work has been done, some heat will be liberated, therefore, the temperature will increase when the small droplets combine together. This could also be explained with a contrary example, that whenever a person get unconscious, we sprinkle water on that person, right? Why we sprinkle water on that person's face? Because when we sprinkle the water droplets, the water we are having in a hole, when we sprinkle it, the water is formed in the water droplets, and when the water is formed in the water droplets, the area of surface area is decreasing, and when the surface area is decreasing, that water droplet has lesser temperature. So when a bigger volume of water is converted into smaller volume, that is the surface area reduces, the temperature decreases. And in this question, the surface area is increasing, so definitely the temperature will increase, right? So the correct answer for question number 16 is option C, that is the temperature will increase. So if you remember the example of that sprinkling water on the face of an unconscious person, you can easily do this without the formula, right? So question number 16 has been done. That is option C. That is when small droplets combine to form a larger droplets. Because of increasing the surface area, the temperature will also increase. Now let's look into question number 17. Question number 17 says that the stress versus strain graph of a wire of two material A and B are shown in the figure. Now if YA and YB are the Young's modulus of the materials, then okay. So see, as we have already told that the slope of the stress strain diagram will give you the Young's modulus. So Young's modulus for A is equals to tan 60, tan 60, which is equals to root 3, right? And Young's modulus for B is equals to tan 30, which is equals to 1 upon root 3. So they are asking you the relation between them. So when we divide this, what we'll get? We will get y a upon y b is equals to root 3 into root 3 upon 1, which is equals to 3 upon 1. So we can say that YA is equals to 3 times of YB, right? YA is equals to 3 times of YB. So we have this in option 4. That is y is equals to 3 times of yd. So from the graph here we can say the correct answer for question number 17 is option D, that is y is equals to 3 times of yd. Now let's get into question number 18. Question number 18 says that a tank contains water on top of the mercury as shown in the figure A. Okay, a cube block of side 10 centimeter is in equilibrium inside the tank. The depth of the block inside the mercury is, they are asking the depth of the block inside the mercury. See, fraction inside is equals to relative density, right? But there are two liquids over here. One mercury is below, then water is above it, right? So, and the body is in equilibrium. It means the buoyant force experienced by the mercury plus the buoyant force experienced by the water is equals to the weight of the mercury, right? So, see, what they have given to us is the given the tank contains the bottom, the mercury density of mercury has been given to us, and water is given to us as density of mercury is 13.6 gram per centimeter cube and density of water is 1 gram per centimeter cube. Now the wooden block is inside, its side is equals to 10 centimeter and the density of wood has been given to us as 8.56. Yes, 8.56 gram per centimeter cube. They have given the density, relative density as 8.56, so its density will be equals to 8.56 gram per centimeter. Now volume of the wood in is equals to side into side, that is side into side into side at 10 to the power of 3 centimeter cube. This is the volume. Now this is floating in the interface of water and mercury of side x and 10 minus x, means x and 10 minus x is here in the diagram. You can see if the length in the water is x, then inside the mercury is 10 minus x, or you can take reverse also. If this is x, then above in the water will be 10 minus x. So the weight of the wooden block, as I told that the block is in equilibrium, therefore the weight of the wooden block will be equals to the weight of the mercury displaced plus the weight of the water displaced. Weight of the mercury displaced means buoyant force given by the mercury plus weight of the water displaced means buoyant force given by the water to the wood. So weight of the wooden block is m into g, right? Mass of the wooden block into g. Weight of the mercury displaced is equals to volume of the wooden block inside mercury into density of mercury into g. Why? Because buoyant force is given as V rho g, where V is the volume of the body inside the liquid, rho is the density of the liquid, and g is the acceleration due to gravity. So volume of the block inside mercury into density of mercury into g plus volume of wood block inside water into density of water into g. Right? Now putting all these value here, y finally calculate and we get the value of x as, we get the value of x as approximately 4 centimeters, right? Well, so what is x? X is the length of the block. X is the length of the block outside the mercury, right? Outside the mercury. So inside mercury it is equals to 6 centimeters. Inside the mercury it is 6 centimeters. So they are asking us the depth of the block inside the mercury. So it is 6 centimeters, right? Now this question can also be done in one way, that see the density, relative density of block. Relative density of block means density of block upon density of water has been given to us, right? And this is equals to 8.56. Now they have given us relative density of mercury. Relative density of mercury means density of mercury upon density of water is equals to 13.6. What we need is fraction inside. Fraction inside the mercury can be given as this. Fraction inside mercury can be given as density of body upon density of mercury, right? Density of mercury. This is density of mercury. So if we need this, if I simply divide this quantity with this quantity, that is, if I do density of body upon density of water divided by density of mercury divided by density of water, this will be equals to 8.56 upon 13.6, right? 8.56 upon 13.6, right? 8.56 upon 13.6, right? So if we do 8.56 upon 13.6, it comes approximately equals to 0.62 something, right? It means 60% of the object is inside. 60% of 10 centimeters, right? This is 10 centimeter, right? So 60% of 10 centimeters is 6 centimeters. So we can get an approximate answer of this question. This is another way. But the reliable way is the first method which we have told you, right? So the correct answer for question number 18 is option 6. Now let's, oh sorry, option A, that is 6 centimeters. Now let's get into question number 19. Question number 19 says the length of an iron wire is L and the area of cross section is A, right? The increase in length is small l on applying a force F on its two ends, right? Which of the statement is correct? The increase in length is inversely proportional to the length. The increase in length is proportional to the area of cross section. The increase in length is inversely proportional to the to area, and the increase in length is proportional to the Young's modulus. See, we have the formula y is equals to f by a upon increase in length small l upon capital L, right? So rearranging it, what you will get, write it like this. You will get y is equals to f into capital L upon small l into a. Again rearranging it, let me write it here. We will get small l is equals to f upon L upon y into a, right? L is equals to f to L upon y into a. So from here we conclude that change in length is inversely proportional to area of cross section. So if area increases, change in length will decrease. So here we have increase in length is inversely proportional to the length. No, increase in length is proportional to the area of cross section. No, increase in length is inversely proportional to the area A. Increase in length is proportional to Young modulus. So the correct answer according to this calculation will be option C, that is increase in length is inversely proportional to A. Here we can see that increase in length is inversely proportional to A. That is we are getting it from the Young's modulus. Now question number 20. Question number 20 says that a horizontal pipeline carries water in streamline flow. Alright. At a point where the cross-sectional area is 10 centimeters square, the water velocity is 1 meter per second and pressure is 2000 pascals. The pressure of the water at another point where the cross-section area is 5 centimeter is, right? Alright. So let the pressure P at the second point and let velocity V is equals to V2, right? Here the pressure V equals to P and the velocity is equals to V2. Now applying the equation of continuity, that is A1 V1 is equals to A2 V2, we get velocity is equals to 2 meter per second. So applying the principle of continuity, A1 V1 is equals to A2 V2, we have A1 as 10, A1 as 10 centimeter square, and V1 is equals to 1 meter per second, and A2 is 5, that is centimeter square. We need to calculate to V2. So 10 into 1 is equals to 5 into V2. We get V2 is equals to 2 meter per second. Right. So velocity here is 2 meter per second. Now see, it's a horizontal pipe. So there is a no change in the potential energy. But there is a change in the pressure energy, and as well as there is a change in the velocity. So there will be change in the kinetic energy. So applying the Bernoulli's theorem, what Bernoulli's theorem says that the total energy of the system remains conserved, that is pressure energy P1 plus kinetic energy half rho V square, that is kinetic energy per unit volume, plus pressure energy, sorry, potential energy rho G H, right? This is equals to initial energies is equals to sum of final energy. Now this rho G H and rho G H will cancel out because the pipe is horizontal and it's not going to change, height is not going to change. Now P1 is given as 2000 Pascal, so we put P1 as 2000 Pascal, half the rho of water is 1000 and V1 is equals to 1 is equals to P we need to calculate, and is equal plus half, again density of water is 1000 and velocity is 2, so square of 2 is 4. Calculating this, we get P is equals to 500 Pascal. So the correct answer for question number 20 is 500 Pascal, that is option C, 500 Pascal. Again, we are using two concepts over here, that is the principle of continuity, A1 V1 is equals to A2 V2, and Bernoulli's theorem, that is pressure energy plus your kinetic energy plus your uh, potential energy is equals to is a constant, that is initial energies is equals to final energies. Using this, we get our pressure at the second end. This end is equals to 500 pascals, right? So what we conclude here is what we can take as a conclusion from here also is that if the velocity is less, pressure is more. If velocity is more, pressure is less. Here we have pressure as 2000 pascals, but velocity is 1 meter per second. Here we have pressure as 500 pascals, but velocity is 2 meter per second. Right? So the correct answer for question number 20 is option C, that is 500 pascals. Now let's come into question number 21. Question number 21. Question number 21 says that the ratio of the length of two wires A and B of the same material is 1 is to 2. That is, if LA is equals to L, then LB is equals to 2 times of L, right? And the ratio of the diameters are this. That is, if RA is equals to 2R, then RB is equals to R. And if this is the case, then area of cross section, if area of cross section of A is equals to 4 pi r square, then area of cross section of B is equals to pi r square, right? Now they are stretched by the same force, then the ratio of the increase in length will be, the force is same. Now the change in length, increase in length is given by the formula we have seen earlier in previous question, that small l is equals to F into capital L upon Y into A. So F is same, material is same, so Y is same. So from here we can say that small L1 upon L2, or we can use LA upon LB is equals to capital LA upon capital LB into A B upon A A. Why? Because it is directly proportional to the length, initial length, and inversely proportional to the area of cross section. Right? So what we'll get? Ratio LA, that is change in length in A upon change in length in B, will be equals to LA upon A is 1 is to 2 into area of cross section. We can see it is 4 is to, this is pi r square, that is 1 upon 4. It will be equals to 1 upon 4. So from here we get L A upon L B is equals to 1 upon A, right? So the ratio will be equals to 1 is to A, right? So I hope this calculation is clear to all. So the correct answer for question number 21 will be 1 is to A, that is option C. Option C is the correct answer, that is 1 is to A, right? We have used the formula small l is equals to f into L upon y into A. What we find that f and y are constant, so change in length is directly proportional to the length and inversely proportional to the area of cross section. So we can say that the ratio of the change in length for A and B will be equals to initial length of A upon initial length of B into the initial area of cross section of B upon initial area of cross section of A. Putting the values, we get ratio as 1 is to A. So the correct answer for question number 21 is option C, that is 1 is to A. Let's come to question number 22. The question number 22 says that the excess pressure inside a spherical drop of water is 4 times that of the another drop. Then their respective mass ratio is. So the inside a spherical drop of water, express pressure is given as P is equals to 2T by R, right? This is express pressure 2T by R. It is given that P1 is equals to 4 times of P2. They are saying that here say the express pressure in the spherical drop is 4 times the that of the another drop. There are two drops. One drop has a pressure P1, then the other has 4 times of P1, right? So P1 is equals to 2T by R1 and this is equals to 4 2T by R2, right? So from here we get R2 is equals to 4 times of R1. We have a relation, we got the relation that the radius of the second drop is 4 times the radius of the first drop. So the mass ratio, we have the radius, it means volume we can get. So mass ratio is mass m1 upon m2, m1 upon m2. So we know that density is equals to mass upon volume. So volume mass is equals to density into volume. Now both are excess pressure of are the droplets of water. So their density will be same. So mass upon mass will be equals to the ratio of their volume. So if their radius are in the ratio 1 is to 4, therefore their mass will be in the ratio, therefore their volume will be in the ratio 1 is to 64, because we have R cube over here, right? So we have R cube over here. So 4 cube is equals to 64. So we have the ratio is 1 is to 64. This is the ratio of the volume, and whatever is the ratio of the volume will be the ratio of mass, right? Let me explain it once again. Here they are saying that the pressure inside a spherical drop of water is 4 times that of the another drop. So pressure inside is given as P is equals to 2T by R, right? Now there are two spheres, that is P1 is equals to 4 times of P2, right? So P1 is equals to 4 times the pressure in one of the sphere is drop is 2 times the 4 times the pressure in another. So we can say that 2T by R1 is equals to 4 times of 2T by R2, right? This and this cancels out. We get R2 is equals to 4 times of R1, right? This is the ratio of the radius. Now, if density is the same, the ratio of the mass m1 upon M2 is equals to V1 upon V2, and V1 upon V2 will be equals to R1 Q upon R2 Q. Why? Because it's a sphere, so the volume of the sphere will be equals to 4 by 3 pi R cube. So R1 Q upon R2 Q. What is the ratio of R1 upon R2? R1 upon R2 is 1 is to 4. So ratio of the volume will be equals to 1 is to 64. And if ratio of the volume is equals to 1 is to 64, ratio of mass will also be equals to 1 is to 64. So the correct answer for question number 22 is option C. That is one. Sorry, option D. Option D. That is 1 is to 64. The correct answer for question number 22 is option number 4, that is 1 is to 64. Now let's get into question number 23. Question number 23 says that an air stream horizontally past an aeroplane. The speed over the top surface is 60 meters per second, and that under the bottom surface is 45 meter per second. Alright, the density of air is given as this, that is 1.293 kg per meter cube. Then the difference in pressure is, see again here the Bernoulli's theorem will be applied. If the air is streaming horizontally, means there is no change in the height, so the potential energy will remain same, but speeds are different, that is 60 meter per second and 45 meter per second. So definitely kinetic energy will be different, and if kinetic energy will be different, then pressure will be different. So we have by Bernoulli's theorem that pressure energy of first, मतलब P1 plus rho GH plus half rho V1 square is equals to P2 plus rho GH plus half rho V2 square. Rho GH and rho GH will cancel out because there is no change in the height. We have V1 as 60, V2 as 45, right? And rho is given as 1.293. So we have rho also. We have P1. We do not have P1 over here. So putting the values, we get the ratio of putting the values, we can easily get P2 minus P1. So P2 minus P1 will be the change in the pressure, right? P2 minus P1 will be the change in the pressure. That is what they are asking. They are asking you the what is then the difference in the pressure. So that is P2 minus P1. So simply what we have the equation finally by Bernoulli's theorem, that is P1 is equals, P1 plus half rho into V1 square is equals to P2 plus half rho into V2 square, right? Now we want P2 minus P1. So P2 minus P1 will be equals to P2 minus P1 will be equals to half rho, we can take it as common, and this is equals to V1 square minus V2 square, right? V1 square, V1 is 60, V2 is 45. Putting the values of V1, V2 and rho, we can easily calculate P2 minus P1 delta P, and on calculation we get delta P as 1018 Newton per meter square. So delta P is 1018 Newton per meter square. That is option A is the correct answer for question number 23. So the basic concept which we have used in this question is the Bernoulli's theorem. Applying Bernoulli's equation, that is the energy remains constant, right? Question number 24. Now question number 24 says that the radius of a soap bubble is increased from 1 upon root pi centimeter to 2 upon root pi centimeter. The surface tension of the water is 39 per centimeter. Alright. Then the work done is, again we can use the formula, tension is equals to work done upon area. Now because it is soap bubble, so it will have two areas, so we will write it as 2. What they are asking the work done. So we can use the formula, work done is equals to tension into 2 times of area of cross section, right? Now what area here represents? This A represents a change in the area. So see, here the calculations are being done for you. W is equals to 2A into T, where A is the area and the T is the tension. So 2 into A is pi, 4 pi. 4 pi. The surface area of the sphere is 4 pi r square. So 4 pi r2 square minus r1 square. This gives you the change in the area and T is the tension, right? Now putting the value, that is r2 will be we put as r2 as 2 by root pi and r1 as 1 upon root pi. Solving this, we will get as 720 earths. Solving this and putting the values, we get work done is equals to 720 earths. So correct answer for question number 24 is option 3, that is 720 earth, right? The basic formula which you use over here is surface tension is equals to work upon change in area. Work upon change in area. The number of areas over here is the soap bubble. If it is a soap bubble, the number of areas are 2, so we multiply with 2 in the denominator. If it was a drop of water, so it will have W upon A only for tension. So putting the value and calculating, we will get the work done is equals to 720 watts, right? The correct answer for question number 24 is option 3. Now let's get into question number 25. Question number 25. Question number 25 says when a certain weight is suspended from a long uniform wire, its length increases by 1 centimeter. That is small l, they have given it is as equals to 1 centimeter. Now if the same weight is suspended from the another wire, the same material and length, but having a diameter half of the first one, then the increase in length will be C. We have seen that L, that is change in length, is equals to F into L upon Y into A. This is the thing, that is the change in length is inversely proportional to the area of cross section. What they are saying in this question is, if the weight is suspended, if the same weight is suspended, means force is same, from another wire of the same material, means Young's modulus is same, and length means L is same, but having a diameter half. If diameter is half, if diameter is made half, area of cross section will become 1/4, A by 4. Area of cross section becomes 1/4. Why? Because area of cross section is proportional to the square of the diameter, because it is pi r square. So area of cross section become 1/4. Once the area of cross section become 1/4, the change in length will be equals to 4 times. So if initially the change in length was equals to 1 centimeter, now the change in the length will be equals to 4 centimeter. So the correct answer for question number 25 is option C, that is equals to 4 centimeters. Simply remembering the formula of Young's modulus, y is equals to F by L upon, that is stress upon strain, F by A, stress upon strain, and from here we calculate L is equals to F into L upon A into Y, right? And from here we get change in length is inversely proportional to area of cross section. So if area of cross section is getting 1/4 or it is reduced by a factor of 4, the change in length will increase by a factor of 4. So if initial change in length was of 1 centimeter, now finally it will change by 4 centimeters. For the second wire, it will be of 4 centimeters. So correct answer for question number 25 is option C. Right? Now let's come to question number 26. Question number 26. 26. 26. Now water drop whose radius is 0.0015 millimeter is falling through the air. If the coefficient of viscosity of air is 1.8 in 10 to the power of minus 5 kg per meter second, then assuming buoyant force as negligible, the terminal velocity of the drop will be. The terminal velocity we have directly formula, we can put into it. The directly formula for terminal velocity V is equals to 2 by 9 rho minus sigma, where rho is the density of the liquid and sigma is the rho is the density of the body and sigma is the density of the liquid, into r square g upon eta. Eta is the viscosity of the liquid. Rho is the density of water, sigma is the density of the air. Why water? Because rho is the density of the substance which is falling. So density of water here, and it is falling in air. So density of density of liquid means density of the medium in which it is falling is sigma. So density of air. Eta is the coefficient of viscosity, and sigma here is negligible because they are asking us to neglect the buoyant force. So if we are neglecting buoyant force, it means we can neglect sigma. So our formula becomes V is equals to 2 by 9 rho r square g upon eta. We have the values, all the values we have rho is given to us as, or we know the density of water is equals to 1 gram per centimeter cube or 1000 grams per 1000 kilogram per meter cube, right? R is R is given to us as 0.0015 millimeters. We can put this as 1.5 into 10 to the power of minus 6 whole square, right? And G is 9.8 and the viscosity is given as 1.8 10 to the power of 5. All the values are given in the question. We have to simply put the values in the formula and calculate it. And while calculating it, we get the final answer as 2.72 10 to the power of minus 4 meter per second. 2.72. 2.72 into the power of minus 4. This is option 1. So the correct answer for question number 26 is option 1. Formula we have used here is V, that is the velocity, terminal velocity is equals to 2 by 9 into rho minus sigma into r square into g upon eta, right? So using this formula, putting the values, we get option number question number 26 as option number 1 correct answer, right? So the question number 27 comes in line. Question number 27. Question number 27 says that when a capillary tube is immersed into liquid, the liquid neither rises nor falls in the capillary. Choose the correct statement for the following. The surface tension of the liquid must be 0. The contact angle must be 90. The surface tension may be 0. The contact angle may be 90. There are 4 options given to us. See, the height of the liquid ascending in a capillary H is given to us as 2t cos theta upon r rho g. Now, if this is 0, see, radius of capillary cannot be 0, density of the liquid cannot be 0, G cannot be 0, right? What we are left is if H is equals to 0, if H is 0, if H is 0, this implies that T cos theta is equals to 0. Now, T cos theta can be 0 if T is equals to 0 or cos theta is equals to 0 and cos theta is equals to 0 means theta is equals to 90 degree, right? So from here we can say that if there is no ascent in the capillary, it means either tension will be 0, sorry, surface tension will be 0 or angle of contact is 90 degree. So it's a it's not a case of confirmation. It may be surface tension or it may be the angle of contact. So we would say that option C and option D are correct. So C and D is correct is given in option 3. So the correct answer for question number 27 is option 3, that is C, that is the surface tension may be 0 or the contact angle may be 90 degrees. So the correct answer for question number 27 is option C from this relation, that is T cos theta is equal to 0. So T cos theta can be 0 only in two cases, whether if the surface tension is 0 or cos theta is 0. If cos theta is 0, it means theta is equal to 90 degree. So H is equal to 0 only in two cases, if either T is equal to 0 or if theta is equal to 90 degree. Theta is angle of contact. So the question number 27 has its correct answer as option number 3, that is C and D are correct, right? Now let's get to question number 28. Question number 28 says that suppose the blood pressure, suppose a blood vessel gets thinner but doesn't branch. Thinner means area of cross section is reducing. Now, which of the following graphs best shows the relationship between the cross section area of blood vessels and the speed of blood flowing through it? See, when it is flow, it's related to principle of continuity, that is A1 V1 is equals to A2 V2, right? What it says that A V is equals to constant, right? If A V is equals to constant means A, or you can say that V is inversely proportional to A, right? So if we are drawing a graph between V and A, that is area of cross section and velocity, right? So here again this It's between velocity and area of cross section. Then it shows an inverse relation. Inverse relation means as the area of cross section is increasing, velocity will be decreasing. So we should first look into the decreasing graph. See, this graph is an increasing graph. Again, this graph is an increasing graph. These two graphs are decreasing graph, among which the inverse relation is properly represented by graph D, right? Which is represented by graph D. So the correct answer for question number 28 should be option D, right? So the correct answer for question number 28 is option D. That is for by what? By what we can say that from principle of continuity we can say that B is inversely proportional to A. So we have the correct answer is option D, right? Now let's come into question number 29. Question number 29. Question number 29 says that A and B are two wires, alright. The wire is the radius A is twice of B. The radius of A is equals to 2 times of radius of B. It means area of cross section of A is equals to 4 times the area of cross section of B. They are stressed by some load. Then the stress on B is, they are stressed by some load. Then the stress on B is equal to that on A, 4 times to that on A, 2 times on that on A, and half of that on A, right? So see, what is stress? Stress is force upon area. Stress is equals to force upon area. So it means stress is inversely proportional to area. So if area of B is 4 times the area of A, it means the stress on B is equals to 1 by 4 times of stress on A, right? So they are asking you, right? Hold on. A and B are of two wires. The radius of A is twice, right? Area is twice. Stress on, see, wait. Let's look into this. Stress is inversely proportional to area, right? Area of cross section. So stress on B upon stress on A is equals to radius of A upon radius of B, right? Radius of A upon radius of B. Right, radius of A upon radius of B. And radius upon A of radius of B is equals to 2. So squaring we get SB is equals to 4 times of SA. SB is equals to 4 times of SA. So the correct answer for question 29 is 4 times that of A. So the stress on B is 4 times of the stress on A. Right. So the correct answer for question number 29 is option B. Let's look into question number 30. Question number 30 says that a solid is completely immersed in an ideal liquid. The force exerted by the liquid on the solid will be, a solid is completely immersed in the liquid, alright. The force exerted by the liquid on the solid will increase if it is pushed deeper inside the liquid. No, it will not increase because it is already completely immersed. So the total volume is inside the liquid. Now if you immerse it deeper, there will be no change in the volume, so there will be no increase in the force. Next, it says the change of its orientation is changed, keeping it inside the liquid. See, if the orientation is also changing, again the volume is not going to change. So if volume is not going to change, the force exerted on the liquid is not going to change. Decreases, that the force will decrease if it is taken partially out of the liquid. Yes, if it is taken partially out of the liquid, the volume inside the liquid will decrease and hence the buoyant force will decrease, because buoyant force is given as V rho G. V is the volume of the body inside the liquid, rho is the density of the liquid, and G is the acceleration due to gravity. If V decreases, the force will also decrease. So the correct answer for question number 30 is option 3, that is it decreases. The force exerted by the liquid on the solid will decrease if it is taken partially out of the liquid. So the correct answer for question number 30 is option 3. Now let's look into question number 31. Yeah. Question number 31, it says an incompressible liquid is flowing through a horizontal pipe as shown in the figure. The magnitude of the velocity V is. Okay, so here the liquid is getting in, again here the liquid is getting in, and here the liquid is getting out. So A1 V1 for the inlet will be equals to A into V of outlet. So using the principle of continuity, we can say that 3A into V plus 2A into 1 is equals to A into 4, right? So from here we get 3AV is equals to 4A minus 2A. So we get 3AV is equals to 2A. AA goes off. We get V is equals to 2 by 3 meter per second. So 2 by 3 meter per second is option B. Option B is 2 by 3 meter per second. So the correct answer for question number 31 is option B, that is 2 by 3 meter per second. We have simply used the principle of continuity here. This is the inlet and this is the outlet, right? So the correct answer for question number 31 is option B. Now let's get into question number 32. 32. It says a rectangular film of liquid is extended from this to this, that is there is a change in the area. If the work done is equal to this, that is 3 to 10 to the power of minus 4 joule, the value of the surface tension on the liquid will be. Again we will use the formula surface tension T is equals to W upon change in length, because it is a liquid film, so area will be equals to 2, so 2 times of area. Surface tension is equals to work done upon change in area. So from here we can say that work done is equals to surface tension into 2 times of change in area, or we are supposed to calculate surface tension. So simply we have work done given to us, and initial area is given to us, and final area is given to us. From here we can change the calculate the change in the area, multiply with 2, put in the value, and we get the answer. That's what we have done over here, and finally we get our answer as C. So work done is equals to T into change in area is initial area is 20, final area is 20, initial area is 8. 5 fours are 20 and 4 twos are 8. So 20 minus 8 into 2, right? Into 2, and 10 to the power of minus 4 is to convert it into from centimeter square to meter square. So finally calculating it, we get tension T is equal to surface tension T is equal to 0.125 Newton per meter. 0.125 Newton per meter is an option 2. So the correct answer for question number 32 is option 2, that is 0.125 Newton per meter. The formula used is surface tension of a liquid is equals to work done upon 2 times of area or cross section or area of the liquid. Why? Because here it is a film, so it has two areas, one area upside and another area down. So we use the formula as 2A. Now let's come to question number 33. In question number 33, the force of 200 Newton is applied at one end of wire of length 2 meter and having an area cross section of 10 to the power of minus 2 centimeters square. The other end of the wire is rigidly fixed. The coefficient of linear expansion of the wire is as alpha is equals to coefficient of linear expansion of the wire is given as alpha is equals to 8 in 10 to the power of minus 6 per degree centigrade. Young's modulus is given as 2.2 into 10 to the power of 11 Newton per meter square, and its temperature by 5 degree centigrade. Then the increase in the tension of the wire will be. So we have F is equals to YA. It is from the Young's modulus formula, and from the thermal expansion we can say the change in length is equals to L alpha delta T, that is the initial length into coefficient of expansion into delta T, right? So from here, this value of delta T we can put it here. Putting that value over here, we get F is equals to Y into A into delta T. Instead of delta T, we are putting L into A into delta T. This is instead of delta L. right? Now we have the value of y, we have the value of a, we have the value of alpha, we have the value of delta t. Delta t is given to us as how much is given to us is by 5 degrees centigrade. So we have 5. So putting the value, we get our answer as 8.8 Newton. That is in option D. What we have done is, again, we have y is equals to F into L upon L into A. So from here we can say that F is equals to y into A into L upon capital L. This is from because of the force applied, and because of the change in temperature we have L is equals to, sorry, change in length. Change in length is equals to initial length into alpha delta t. So this value of small l, when we put it here, we get F is equals to y into A into L alpha delta t upon L. This L and L goes off. We finally left with is F is equals to y a alpha delta t. Right? This delta t is given to us as 5. Alpha is given to us as 8 into 10 to the power of minus 6. Area of cross section is given to us as 10 to the power of minus 2 per 10 to the power minus 2 centimeter square, and Young's modulus is also given to us. All the values have been given to us. Putting these values in the question, in the formula, we get F is equals to 8.8 Newton. That is option D, right? Now let's get into question number 34. Question number 34. Question number 34 says that a streamline flow is more likely in a liquid. See, streamline flow is more likely in a liquid with a low density and high viscosity, right? So it is option 2, right? Option 2. The streamline flow can be easily observed in a liquid of low density and high viscosity. So the correct answer for question number 34 is option 2. You have to remember it. Then the question number 35. Question number 35 says that a air bubble rises from the bottom of a lake to the surface. Now, if its radius increased by 200% and atmospheric pressure is equal to the water column of height h, then the depth of the lake is. So let's look into the calculations. This is change in the radius, that is r dash minus r upon r is given as 200%, so we write it as 200 upon 100. So from here when we calculate, we get the new radius of the air bubble is equal to 3 times of the initial radius, right? Now volume of the bubble is equal to 4 by 3 pi r cube. When radius is increased, the new volume will be equal to 4 by 3 pi 3 r cube, right? So from here we get that the new volume is 27 times of the old volume, right? Now density rho gh, rho gh is the pressure of the water column, which is equal to the atmospheric pressure, because here they say that the atmospheric pressure is equal to the water column height. So atmospheric pressure is 10 to the power of 5 Pascal, and this is equal to pressure because of water column. So pressure because of water column is given as density of water into height of water column into g, right? So density of water is equal to 10 to the power of 3 into h we need to calculate, and g is to be taken as 10. So this is 10 to the power of 4, and here we have 10 to the power of 5. So h we get as 10 meter, right? H we get as 10 meter. Here we get h is equal to 10 meter. Now P1 V1 is equals to P2 V2. So P1 V1 is equals to P2 V2. We need to calculate P1, that is the initial pressure. We have volume V1, initial volume, that is 4 by 3 pi r cube. P2 is 10 to the atmospheric pressure into new volume is 27 times of older volume. Calculating this, we get P1 is equals to 27 into 10 to the power of 3, right? So the pressure outside, total pressure outside is equals to 27 10 to the power of 5 pascals. This is equals to atmospheric pressure plus pressure because of water column. So finally calculating it, we get H dash is equals to 26 times of H, right? So the depth of the lake is 26 times of H. The correct answer for question number 35 is option 4. Now let's get into question number 26. 36. Question number 36 says, assertion, it says, smaller drop of liquid resists deforming force better than the larger drops. Excess pressure inside a drop is directly proportional to the surface area, right? So the correct answer for this is option C. That is, the assertion is true, but reason is false. Why? The small drop of liquid resists deforming force. Why? Because the excess pressure in the drop P is given to us as 2T by R. That is, smaller is the radius, greater will be the pressure, and greater is the pressure, more will be the resistance of change in uh, more will be the pressure, more will be the resistance for the deforming force, right? So smaller is the drop, more will be the resistance for the deformation of the drop. But it is because of the radius, right? It is because of the radius, not because of the surface area. So reason that excess pressure inside a drop is directly proportional to the surface area. No, it is inversely proportional to the surface area. It's not directly proportional to the surface area. It is inversely proportional to the surface area. So the reason is wrong. So assertion is correct, reason is wrong. So we get correct answer is option C. So now let's get into question number 37. Question number 37 says that if a spring is extended to length L, then according to Hooke's law. Now, if spring is according to Hooke's law, see, according to Hooke's law, within the elastic limit, the stress is directly proportional to the strain. So we can say stress is proportional to strain, and stress upon strain is a constant, right? Now, this constant is proportional to the proportion is called as Young's modulus, all right? So we have this Young's modulus y is equals to f into L upon small l into a, right? Now the area, total length, and the modulus distance. Now we have this f can be written as y into L into a upon capital L. So from here we can say that f is equals to y into a upon capital L into small l. Now all these things, that is Young's modulus, area of cross section, and length, all these three quantities are constant. So can I write it by k? So finally we get f is equals to k into L, right? F is equals to k into L. So for a spring, we can say that F is equals to K into L, where K is equals to YA upon L. So the correct answer for question number 37 is option K into L, option A, right? Option A. Now let's get into question number 38. Question number 38 says that a thin flat circular disc of radius 4.5 cm is placed gently over the surface of water. Now, if the surface tension of water is 0.07 Newton per meter, then the excess force required to take it away from the surface. Now the excess force is equals to tension, surface tension into surface area, right? Because surface tension is, sorry, this is circumference. What is surface tension? Surface tension is force per unit length. So if we need to calculate force, we'll have to multiply the surface tension with length. So surface tension is given to us as 0.07 Newton per meter, and radius is being given to us 4.5 centimeter. From radius we can calculate the perimeter of the circle, that is circumference of the circle. So putting the value, we get our force as 19.8 millinewton. 19.8 millinewton is 38 is option C, that is 9.8 millinewton, right? What we have used is surface tension P is equals to force per unit length. So force will be equals to surface tension into length. Length over here is equals to 2 pi r. Length is equals to 2 pi r, that is the circumference of the disc, right? The correct answer for question number 38 is option C. Now let's come to question number 39. The pressure experienced by a swimmer 20 meters below the water surface in the lake is approximately. So pressure inside the liquid, pressure at any point inside the liquid is given by the formula rho g h plus atmospheric pressure P naught. Rho is being given to us, G is being given to us, and H is also given to us, and P naught, that is atmospheric pressure, is also given to us. So atmospheric pressure is equals to 10 to the power of 5 Pascal, H is equals to 20 meter, Rho is equals to 1000, and G is equals to 10. Putting the values, we get this P is equals to 3 atmosphere, right? So the correct answer for question number 39 is is 3 atmosphere, that is option C. Now let's get into question number 40. Question number 40 says that an incompressible and non-viscous liquid flows through the horizontal tube of different cross-sectional area as shown in the figure. The velocity v of the fluid is. Again from the diagram, what we are supposed to do is we are supposed to apply the principle of continuity. So it is area of cross-section is small a and velocity is 5. This is inlet. Outlet is a into 2 plus v into a by 4 plus 2.5, write it like here, it is equals to 2.5 into a by 2, right? So we have a common here, so we'll get a and a cancelled out. What we are left with is 5 is equals to 2 plus 1.25 plus b by 4. So 5 minus 3.25 is equals to v by 4. So 5 minus 3.25 is equals to 1.75 is equals to v upon 4. V is equals to 1.75 into 4. This is equals to, we get it as 7 meter per second. So V is equal to 7 meter per second. So correct answer for question number 40 is option 2, that is 7 meter per second, right? So we have simply applied the principle of continuity. This is A into 5 is inlet and the rest of the things are of outlets, right? So the question number 40 as the correct answer is option number 2. Then let's come to question number 41. Question number 41. When a pressure of 100 atmosphere is applied on a spherical ball, then its volume reduced to 0.01%. So the bulk modulus of the material of the rubber in dyne per centimeter square is. See, there is a reduce in the volume is given as 0.01%. It means they are saying delta V upon V is equals to 0.01 upon 100, right? Delta V upon V is equals to this much. They are asking you bulk modulus, and bulk modulus is given as, we can write it as B or K. Bulk modulus is equals to your pressure upon change in volume upon volume. Pressure is given as 100 atmosphere. So bulk modulus B will be equals to 100 atmosphere upon delta V upon V is equals to 0.01 upon 100. So into 100, right? Removing decimal, we will get 2 more zeros. So bulk modulus will be equals to 10 to the power of 6. 10 to the power of 6 Newton per meter square, or yes, 10 to the power of 6 Newton per, 10 to the power of 6 Pascal, a Newton per meter square, or you can say Pascal, right? Now we need the answer in dyne per centimeter. So 10 to the power of into 10, right? No, 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 it's 100 atmosphere, na? It's 100 atmosphere. So we get bulk modulus as B is equals to 10 to the power of 6 atmosphere, right? And 1 atmosphere is equals to 10 to the power of 5. It will be equals to 10 to the power of 11 Newton per meter square. Now 1 Newton per meter square is equals to 10 dyne per centimeter square. So this will be equals to 10 to the power of 12 dyne per centimeter square. So the correct answer for this will be equals to option C, that is 10 to the power of 12 dyne per meter square, right? See, uh, from this, when we put the value, how we are putting the value, let me show you. So we have B is equals to pressure. Pressure is 100 atmosphere. So 1 atmosphere is 10 to the power of 5. So 100 atmosphere will be 100 into 10 to the power of 5 Pascal upon delta V upon V is equals to 0.01 upon 100. So we'll multiply with 100 over here. So we are removing decimal from here. We'll have to multiply one more 100 here. So all total number of zeros over here is 2 plus 2 is 4 plus 2 is 6 and plus 5 is 11. So we get bulk modulus is equals to 10 to the power of 11 Newton per meter square. Right? Now, see, 1 Newton is equals to 10 to the power of 5 9, and 1 meter square is equals to 10 to the power of 4 centimeter square. So 1 Newton per meter square will be equals to 10 dyne per centimeter square. So we have to convert this into dyne. We will simply have to multiply with it, 10. So this will be equals to 10 to the power of 12 dyne per centimeter square. So the correct answer for question number 41 is option C, which is equals to 10 to the power of 12. Right. So the correct answer for question number 41 is option C. Let's come to question number 42. Okay. Now question number 42 says, question 42 says that a tank is filled with water and two holes A and B are made in it as shown in the figure. For getting the same range, ratio of the height h dash upon h. So see, if you look into this diagram, they say that let the gap between the A and B is equals to x. Let this equals to x, right? Let this gap is equals to x. For hole A, the velocity of efflux is equals to under root 2 g h plus h dash plus x, right? And the range is equals to 2 root h into x plus h dash. Now for B, the velocity of efflux will be equals to under root 2 g h dash, and range will be equals to 2 under root h into x plus h dash into x plus h, right? Now, but the range for the liquid for hole A and B are equal. So we'll equate the range. That is, we'll equate equation 2 and equation 1. And from here equating, we'll get h dash is equals to h. H dash is equals to h. So the ratio will be equals to 1 is to 1. So the correct answer for this question will be equals to option 2, that is 1 is to 1. Question number 43. The velocity of efflux from a same hole made in the bottom of the corner as a function of height y of water level in the tank is given given as a straight line, because velocity of efflux is given as v is equals to under root 2 g h, right? So this is an equation of a straight line, so it will be a straight line. So the correct answer is option 1, right? This will be a straight line. Then question number 44. Question number 44 says that the pressure applied for all directions on a cube is P. How much should its temperature be raised to maintain the original volume? The volume elasticity of the cube is beta and the coefficient of volume expansion is alpha. If the coefficient of volume expansion is alpha and the rise in temperature is delta theta, then delta V is equals to V into alpha delta theta, right? Then from here we can write that delta V upon V is equals to alpha delta theta. Now the bulk modulus is given as P upon delta V upon V. So we put the value of delta V upon V from here into it. We will get bulk modulus B is equals to pressure upon alpha delta T. Now we need to calculate delta T. So delta T or delta theta will be equals to P upon alpha beta, right? So delta theta is equals to P upon alpha beta. So the correct answer is option A. Option A is the correct answer of question number 44. Now let's get into question number 45. The velocity of a small ball of mass m and density d when dropped in a container filled with a glycerine becomes constant after some time. Now if the density of the glycerine is d by 2, the viscous force acting on the ball will be. So when the ball is being dropped, there are forces acting on it is, if suppose the ball has been dropped, the force acting on it is mg, and in the upward direction it is the viscous force Fv, and is also the buoyant force, that is Fb. And if they say that it is moving when dropped in a container, the glycerine constant between contact after some time become constant. The velocity is constant. It means it is in equilibrium, that is mg will be equals to Fv plus Fb. So here mg is equals to Fb plus Fv. So the viscous force is equals to mg minus b. From this free body diagram, we can write mg is equals to Fb, that is buoyant force, plus viscous force. So from here we can say that the viscous force is equals to mg minus the buoyant force, right? The buoyant force. The buoyant force is given as volume of the liquid, volume of the body inside, that is V, and rho is the density of the liquid, and G is the acceleration due to gravity. So putting the value, we get, and mass, we are taking mass is equals to density into volume. So Fv is equals to density into volume into G minus density into volume into G by 2, right? Why G by 2? Because we see that the density of the glycerine is D by 2. So here for the buoyant force we will use the density of the liquid, which is equals to density by 2. Now further calculating it, we will get Fb is equals to mg by 2. So the correct answer for question number 45 is option 2, that is mg by 2, right? Question number 46. Water and oil are poured in the two limbs of U-tube containing mercury. The interface of the mercury and the liquid are at the same height in both the limbs. Means this height is the same. This height and this height is the same. The height H2 is equals to 20 centimeter and the related density of the oil is 0.9. When then the value of H1. This is H1. We need to calculate this. See, if this is at the same level, it means the pressure at this point will be equal to pressure at this point. So pressure at this point, that is pressure at A, will be equal to pressure at B. Now pressure at A will be given as rho G, as that is density of water into G into H1, and pressure at B will be equal to density of oil into G into H2. We are supposed to calculate H1, so we can say that H1 is equals to density of oil into G into H2 upon density of water into G. So G and G cancels out. Density of oil upon density of water is nothing but relative density of oil, which has been given as 0.9, right, into H2. H2 has been given as 20. So 0.9 into 20 will give you 18, right? So it will be 18 centimeters. So H1 will be equal to 18 centimeters. The correct answer for question number 46 is option 1. Question number 47. Question number 47 says that a cube of aluminium of side 0.1 meter is subjected to a shearing force of 100 Newton. The top face of the cube is displaced through 0.02 centimeter with respect to the bottom face. The shearing strain would be, so shearing strain is, if suppose this is the cube, and after application of the force it gets shifted like this, right, and this is given as 0.02, and this is given as how much, 0.1. This is in centimeter and this is in meter. So 0 point meter is equals to 10 centimeter. So shearing strain is equals to shift upon height. So it will be equals to 0.02 centimeter upon 10 centimeter. This will be equals to 0.002. So shearing strain would be 0.002, which is option 4. Option 4, right? Question number 48. Question number 48 says that a spherical object is dropped inside the viscous liquid. Choose the correct velocity versus time graph of the object, where Vt is the terminal velocity. See, when an object has been dropped inside it, its velocity first increases, right? And then it gradually becomes constant, right? Because it faces the opposing forces of force of viscosity and buoyant force. So here we can see that the velocity is increasing with time, so this cannot be done. It's increasing, but it's not getting constant. Here we have some initial velocity and then it is gradually getting constant. Let's see more. So it is decreasing. No, it increases first. So again, this is also not the correct graph. The velocity increases first and then it gradually becomes constant. So it is increasing and gradually becoming constant is option 3. Here it is increasing and finally decreasing. No, it's not this, because velocity get a constant value at terminal velocity. So the correct answer for question number 48 is option 3. Why? Because when a body is being dropped, it is first experiencing the acceleration due to gravity, because of which it increases its speed, and as it comes in the contact with the liquid, it experiences a viscous force Fv and the buoyant force Fb, and a time comes when the weight of the liquid is being balanced by these two forces, and that is the point where the terminal velocity comes in existence and the body is in equilibrium and it moves with zero acceleration, right? So that could be represented well by this graph, that is in option 3. So the correct answer for question number 48 is option 3. Now let's come to question number 49. Question number 49 says that a large bubble rises from the bottom of the lake to the surface and its radius becomes 4 times. Find the depth of the lake in atmospheric pressure is equal to the column of the water column. So again, By Boyle's law, P1 V1 is equals to P2 V2. P1 V1 means when it is below the lake. So below the lake, the pressure is equals to atmospheric pressure plus rho GH into volume is equals to 4 by 3 pi r cube. And outside is the pressure P naught, that is only the atmospheric pressure, and the volume is equals to 4 by 3 pi r cube, and here is r is 4 times of the radius inside the liquid, right? Initial radius. The final radius is 4 times the initial radius. Now from here we get P naught plus rho g h is equals to P naught into 64, right? So from here when we calculate, we get our rho g h is equals to 63 h. So the correct answer for question number 49 is option 4. See what has been done over here is your 4 by 3 pi r cube, and this is 4 by 3 pi r cube. So what we get from here is P naught plus rho g h into 4 by 3 pi r cube is equals to P naught into 4 by 3 pi r cube into 64, right? Into 64. Why? Because radius is 4 times, so 4 cube is equals to 64. Alright, and this is like this. So this is P1 into V1, right? So from here 4 by 3 pi r cube, 4 by 3 pi r cube cancels out. What we are left with is P naught plus rho g h is equals to 64 P naught. So we get rho g h is equals to 63 P naught, and P naught is taken as rho into G into capital H. So this and this goes off. What we are left with is 63 times of capital H. So the correct answer for 49 is option 4, that is 63 H. Now question number 50. Question number 50 says that a graph is shown between the stress and the strain of a metal, the part in which the Hooke's law is hold goods. So Hooke's law states that stress is directly proportional to strain, right? And the slope gives the Young's modulus. And this means there should be a straight line in the graph. So OA region is the region which has a straight line. So OA is the region which represents the Hooke's law. So the correct answer of question number 50 is option 1, right? That is OA represents the Hooke's law. So all solutions for the question, all question 50s are done. I hope the explanation for all the questions is clear to all. Thank you.